طيب السلام عليكم everybody. Welcome to the introductory course of AE221 Introduction to Aerospace Engineering presented by the Aerospace Engineering Club at KFBM. So starting off, in this course we'll be learning about some basic information about aerospace, and generally we have some criteria like control, propulsion, aerodynamics, and structure, astrodynamics, and so on. So in this course, it will be presented by a couple of instructors, and here are the instructors that made these slides, which is Dr. Suhail. There is the office hours, as you can see. So this is the textbook that you are going to take alongside some other problems from in the structural chapter, which going to be mechanics of materials. But in this book that we have already studied at, it did not contain anything regarding structures. So maybe in the next upcoming versions, you might have structures chapter. So here are the syllabus. As you can see, the distribution of grades, it might be different from yours, but this was ours. So here is the plan that you are going to take alongside this course. We have here chapter 1 and 2, the introductory chapters, and then 3. Then we will start with aerodynamics, and then wings and airfoils, elements of airplane and performance, which is control, then control and stability, flight structure and materials, and then propulsion, last but not least, space flight. And also you might take structures. You can refer to mechanics of materials book. So starting off, what is aerospace engineering? So in general, aerospace engineering, you need to work with anything that flies, maybe through air, through space itself. So anything that has flight motion, aerospace engineers also can work with. So aerospace engineering has two main criteria: aeronautical engineering and astronautical engineering. Basically, aeronauticals works with anything that flies within the atmosphere, and astronautical engineering works with anything flies outside the atmosphere. So there are many criteria that an aerospace engineer can work in, like propulsion, satellites, defense, also applications, design, research. It's not only, not like they say, only airplanes and stuff. And this is a distribution of where can an aerospace engineering work. It's too general. It might be different from time to time. So let's start with a history of aerospace. So first we can start with Leonardo da Vinci himself. So Leonardo da Vinci, as we all know, he was an innovator. He made some inventions. He failed some and was successful in some, but he wasn't lucky with anything regarding flight. Some say that he broke some bones and ribs while trying to achieve the succession of flight. And then we have the Monofloia brothers, Joseph and Ethne. They made the first hot air balloon, as you can see here in this picture. They have flight for some time above Paris, and they were the first manned flight, but not on an airplane. And then, most importantly, Sir George Cayley. He was the first man to make a simple structure of, or the man who made the structure that we are using for today, which has some fuselage and tail to control. And then comes Felix du Temple and Alexander Mozinski, which is a Russian and French friends. They worked together to make the first powered hops. What is a hop? A hop is a motion where you go up and down, just like a bunny hop. So they did not fly sustainedly for a long time. They just made some hops. And then we have Otto, who made the first successful gliders. Difference between a glider and a flight vehicle. A glider, you need to be at some elevated height, and then you jump from this height and you glide for some time. And as we can see here, the sketches of George Cayley. Here is the fuselage, and here's the tail. Basically, this structure we work within for today. We add some wings and stuff, but this is the basic structure. We have some fuselage and a tail. And as you can see here, the evolution of his sketches. And then we have Samuel, the first sustained heavier than air flight. But it was unmanned, so only the airplane itself was flying without any man within it. Then comes Oliver and Wilbur, right? These brothers. So these brothers achieved the first sustained heavier than air manned flights in the history. So basically, what they say, two brothers were on a hill, and then one brother was riding the vehicle itself, and the other brother was running beside him, so he can make sure that his brother is safe. And after all these innovations by all these scientists, we have developed our aeronautics until today, and it is under development as well. As you can see here, the development of the aerospace engineering sectors. We started from simple gliders, and we have made it to unmanned, fully controlled UAVs. So there are three ways and principles of how flight is achieved. So first, we have difference in density, where the hot air is lower in density than cold air, so the hot air goes above. And then we also have pushing air downwards, where the air comes from this side, and then it stops by here. The natural tendency of air itself going from a higher pressure area to a lower pressure area here above the wing. And then also we have the third Newton law, where we have some force acting downward. It will have a backward motion. And then there are the fundamental thoughts of aerospace. There are some gas laws, sources of aerodynamic forces, and also units, anatomy of airplanes, and also anatomy of space vehicles, equation of state. These will be covered in this chapter. So starting from fundamental physical quantities, we have 4 fundamental physical quantities for aerodynamics. Not only aerodynamics, but are used very often in aerodynamics sector. Pressure, density, temperature, and velocity. So starting out from pressure, as we all know, pressure equals force over area. And here the force is concentrated on this block. So to have the pressure on this block, we need to have the force over the area. And then we go to density, and also, as we know of density equals mass over volume. So here we have the volume of this block and the mass of the block. So we divide the mass of the block over its volume. Regarding also the units, pressure has newtons over meter squared, which is also equals to Pascal. This is a derived unit. And density is just kilogram over meter cube. I don't think there is any other derived units. Then there is temperature. Temperature basically is the measure of the kinetic energy of the body itself, and we can achieve it from this law. Or if you want to get it specifically, you can have K kinetic energy multiplied by 2 over 3 multiplied by the Boltzmann constant, K. The Boltzmann constant is constant for all gases. And also the temperatures need to be in Kelvin. And there we have velocity. There are some differences between velocity and speed. Speed is a unit, a scalar product, a scalar quantity, and velocity is a vector quantity. So basically in this course, we're only going to have velocity. We're going to work with velocity. So basically velocity equals distance over time. And now, as we can see, here is an airfoil. So what is an airfoil? So let's say we have this airplane, and there will be the wing. So an airfoil, I know this drawing isn't great, but the airfoil is the cross section of the wing, and you can see it here. So let's take it step by step. So here is the air particle at velocity, the initial velocity itself. Then it moves forward until this point where it is called the stagnation point, where we have zero velocity because it came in contact with the airfoil itself. And it has the highest pressure from all the points here on the airfoil. And then after the initial velocity, it becomes normal velocity here above the airfoil itself and has increased velocity as well. So visualization of the velocity on the streamline itself. Why is it important? As we can see here, as mentioned before, we have higher density of pressure here and lower density here. So sorry, high pressure and low pressure. Let's rephrase it again. Yes, so when we visualize, why is it important that we need to visualize the airfoil itself? So visualizing the airfoil itself give us a traditional idea of how an airfoil can work. So as we can see here, here is a turbulent flow, which will be discussed later on, inshallah. And here we have a laminar flow. So here underneath the airfoil itself, we have a condensed amount of particles, which has a higher pressure than on top of the airfoil itself. So as we have said before, air itself has a natural tendency of going from a higher pressure to a lower pressure area. So there will be created some lift upward. These will be, inshallah, proved later on in next upcoming chapters. So there are two main sources of aerodynamic forces that act on the airfoil itself, but they will be broke on in the next upcoming chapters, I believe chapter 5 or 6. But here are the two main factors. It is pressure distribution because of the air itself on the airfoil, and there is the shear stress. What is a shear stress? When an air particle goes along the airfoil itself, it has some frictional force here, so it will reduce the speed of the airfoil itself when the airfoil or the airplane itself going forward. Also, here is the note. The length of the arrow denotes the magnitude of the pressure. So the equation of state, probably the most important equation in this chapter. It is used, this version of it is used for the perfect gas. And we know the perfect gases are the last column of the periodic table, or most commonly here in this course, air on the high altitudes. It will be proved or considered as perfect gas. So P pressure equals rho density multiplied by R, which is a constant, multiplied by the temperature. And the gas constant is, as you can see here, it will be provided also in the formula sheet. And there is the equation of state also, but for for a non-perfect gas, like all the other gas particles, all the other gas elements in the periodic table, other than the 8th column. Here, B and A represent a gas constants. They must be given in the question, or one of them must be given, the other must be found. So pressure and density temperatures under standard conditions. What is a standard condition? Standard condition is when we talk on the surface of Earth. And what is the standard Earth surface? It is the sea level. So sea level is considered the standard conditions. So here are the standard conditions on the sea level. So let's solve the example one. Compute the temperature in a point on a wing of a Boeing 747, where pressure and density are given to be 0.7 multiplied by 10 to the power of 5 newtons per meter square, or also we can call it Pascal. and 0.91 kilogram, the density 0.91 kilogram per meter cube. So we also have the perfect gas law, P equals rho R T. So the temperature is wanted, so we can have T equals pressure over rho R, and then T equals pressure is 0.7 multiplied by 10 to the power of 5 over 0.91 multiplied by, as we have mentioned before, the gas constant is 287.05. 287.05, and this should give you this result. And to convert it to this result, you only subtract 273 point, I think 15, I'm not sure. And then next example, compute the total weight of an air, just let's delete this part. So compute the total weight of air in a room of dimensions 30, 15, and 5 meters under standard atmospheric conditions at sea level. So he mentioned here the standard atmospheric pressure, so these conditions are applied. Okay, so first, the density equals mass over volume, and thus mass equals density multiplied by volume. Now let's calculate the volume first. So the volume is 30 by 15 by 5. This will give us 2,250. And now M equals rho, which is given to us here in standard conditions 1.225 multiplied by 2,250. This will equals to 2,756 kilograms. So the specific volume is the inverse of the density itself. And hence we have the equation of state as before, P equals rho RT. We can also convert this volume into the density into P equals 1 over volume, specific volume RT. So let's start with the motion of the airplane itself. So we have yaw and pitch and roll. So yaw is when the airplane itself goes left or right. Okay, this is what's called yaw. Now, what is pitch? Pitch, it's going up or down. And roll, when the airplane itself, the whole airplane, like let's say from the wings, goes rolling on the fuselage itself. So it rolls in a specific axis going through the fuselage. So the parts that control the yaw are mainly here in the tail itself, vertical stabilizer and the rudder. And there is the elevator, which controls the pitch. We also have some parts here that also control affect the pitch. And we have here on the wing flaps, ailerons, and spoilers. Spoiler and flaps and slats have to do with lift and drag to either increase the lift or increase the drag. Also, we have ailerons to change the roll. And there is the cockpit, which is the front end of the fuselage itself. And also we have the fuselage itself, which is the main part of the airplane, which has the package or the payload or whatever. And we have here the turbine engines, and there's the wing itself, and the winglet. What does the winglet does? What is the function of the winglet itself? So a winglet, or just a wing without a winglet, we have here under the wing, we have wind vortices. that go all around the wing itself. So to interrupt this motion, so we don't have any downwash on the wing itself, we have the winglet, as you can see here. And now the anatomy of the wing and the fuselage. So mainly all the parts of the wing or the airplane itself needs to have a skin. Probably most of the aircrafts have a skin thickness of between 1.5 to 1 millimeters. And as you can see here, here is the skin. Longerons is a long rod that goes throughout the whole structure. Frames to give shape to the skin. All of them together are called monocoque. A semi-monocoque. If there is no any structure inside, just only the skin, it is called a monocoque. These details will be discussed later on in the structure chapter. There are the stringers, which connect the frames together, and also bulkheads. And now the wing itself, we have wing root, which is connected to the fuselage, and the wingtip, the end of the wing itself. And we have leading edge. It is the first front face of the wing, and the trailing edge, the other end part of the wing. Also, we have a spars. Most of the airplanes or the wings, on big airplanes have 2 spars, as you can see here. And in smaller aircrafts, they only have 1 spars. And there is the rib that gives the shape of the wing itself. And we can see here also the same the structures that we have discussed yet before. Now let's start with the anatomy of space vehicles. So space vehicles generally, or this kind of space vehicles, the space shuttles, are not used for nowadays because they are expensive, inefficient, and also non-convenient. But you can see here some of the structures in the space shuttle have the same structures here in the airplanes. And here we have the rockets themselves. Some rockets are made of liquid propellants and others are made of solid propellants. We will discuss later in the propulsion chapter the main difference between liquid propellants and solid propellants. You can see here, this one is the solid propellant and this one is the liquid propellant. So a solid propellant contains of only one type of fuel, and once it is ignited by the spark, it cannot be shut down, unlike the liquid propellants, which can be shut down just to cut supply from the oxidizer and the liquid fuel. But the main problem of the oxidizers and liquid fuel, they are first need to be kept in very cold conditions. They are not safe to work with. And also, the only main advantage from the liquid propellants is that you can cut off the ignition itself. And the rest of the chapter will be discussed. Some questions of the chapter will be solved by Muhammad al-Busayri, inshallah, and on a different video.